Okay, good morning, everyone. Seems to me something's wrong with the recording indicator over there. So anyway, hopefully it's working. Just to give you guys a quick update about assignment. We got 3 tutors. Of course, there are also the 3 markers marking the first assignment. And yesterday, I get a quick update from the 3 guys. Excuse me. And they are working very hard on the first assignment. Some of you probably already got your market assignment back, but most of them will get by the end of this week, if not all. So the deadline we set for finishing our assignment marking is Thursday next week, in 1 week time. But I believe most of them, if not all, will get your market assignment back by Sunday. All right, this Sunday. This is about the first assignment. Second assignment, the second assignment will be released today. The reason why, actually it was already for a few days, the reason why I'm holding the second assignment is because the second assignment will use one data structure, which is binary search tree, that is covered today. So I don't want to, I would like to hold this one until I have already talked about binary search tree. Otherwise, some of you may come to me, oh, what's the binary search tree? How should I do that? All right, so that's the reason. In the beginning of next week's lecture, please take a close look of the assignment specification. Oh, by the way, the second assignment will be, the first one was individual, and the second one will be in a group of 2, all right, basically. But if you have difficulties finding a partner, for example, you're working full-time, it's very hard to find a partner which have the same, time, to working on the assignment. You can do the assignment by yourself, right? It's okay. I specified it very clearly in the beginning of the assignment specification, so take a quick look. But if you are keen to working individually or working by yourself, then the marking criteria that were used for marking assignment will be exactly the same. Still the group assignment requirement. We will not, compromise, reduce any working load for individual. So because this is your choice, right? So I strongly encourage all of you, if possible, working in pairs, okay, for the second assignment. Right, I will talk about more next week, but please take a look of the second assignment specification before coming to this lecture next week. So if you have a question, yeah, I'm happy to take questions, any questions, about the second assignment. All right, and also in the post survey, I got quite a few. First of all, thanks all of you who participated in the survey, and the result and the comments, generally speaking, are pretty encouraging, pretty good. But I do got quite a few, comments for this unit. One of them, some of them, is not very consistent. For example, there's one guy said in the comments, said, this unit is about data structure and algorithms. By the way, in the first few weeks, we spent too much time talking about C++. Where there's another guy say, I would like to more, I love C++. I don't want to talk about too much data structure and algorithm. So it's, but anyway, so it's what I'm trying to say is it's very hard to make everybody happy, because when you come to this unit, probably your expectations are different. Some of them are very confident with C++ already. They're coming for data structure and algorithms, where others are probably more interested in C++ programming. All right, this is one thing. Another comment which actually made by 2 or 3 students was in the first few weeks, I didn't finish the lecture in time. That's true. So can I take this opportunity to give you guys explanation? Because in the first few weeks, actually, I knew sometimes, we run out of time because of a lot of reasons. But the bottom line is I make sure I covered all the contents, all the knowledge and skills, all the content that needed to be used in that week practical. So that's bottom line. To be honest, in the first few weeks, I was not worried about the timing issue, because as long as we cover all the core covered. But I think your comments are right, no problem. So as you can see, I'm improving. So every week I can definitely finish my lecture in time. That's for sure, no problem. If I want to do that, I can do that. But sometimes why I, just delay a little bit, because I want to talk about some topics which are maybe interesting to your guys. That's why, So that's why I will take a lot of questions during the lecture. Anyway, I think the comments are all good. So thanks for that, and I'll definitely pay more attention for the timing, time management, in the rest of semester. Okay. Okay. Now, this week we talk about, so basically the second half of the lecture, the second half of the semester, is about algorithms and data structures, right? So today we are talking about where I will introduce 3 new data structures to your guys. Of course, when we talk about data structure, we also need to talk about algorithm as well, as you will see in a minute, right? For example, the operations defined on particular data structure. So they are related to algorithms. For example, Traversal, which you have already talked about previously, and we will talk about again in today's lecture, right? So just as an example, searching, that's another very popular operations or algorithm, defined on different type of data structures. Today we are also talking about data structures, searching, for example, algorithms on 3 different data structures, all right? And because, as I mentioned earlier, binary search tree is our data structure that you need to use in the second assignment. So today's lecture, I will spend most of the time on that. And also we're talking about tree. That's another reason, that because binary search tree is probably one of the most popular data structures, right, used in software development, right? So there's another reason. But we'll also spend a few minutes to talk about the tree, and very briefly talking about the third data structure, which is a map. Why only talk about very briefly about a map? That's not because it's not important, but because in today, or some people, to do this practical corresponding practical next week, because of the public holiday, there is quite a few questions about a map, right? So what I'm going to do for map is just to give you some introduction, what is a map, the interface, and so on. So there are a lot of implementation details you need to do in the practical, in the workshops, all right? That's the reason. Okay. The first one, binary search tree. Before talking about, before telling you what is a binary search tree, I need to introduce another concept, which is related to binary search tree, and it's called a binary tree. So no, binary search tree, binary tree. So what is a binary tree? Binary tree of course, a data structure, right? So we talk about in the context of computer science. So binary tree is a data structure. Actually, it's a sort of a container, just similar to vector, similar to array, similar to stack, and queue, which is used to hold a number of other items. Generally speaking, same size, same type. All right, it's a sort of container. It holds a lot of other items or data. All right. And binary tree is a data structure, right? That's number one. Number two, why is it called a binary tree? Because if you look at this, that's just an example instance of a binary tree. As you can see. Of course, the root is at the top, not at the bottom. It's going downwards, not upwards. So these are slightly different. If you rotate 180 degrees, this would be look pretty much like a tree, right? So the root is at the top. For example, for this one, a node, we call node. This is node. There are sort of two kind of components in a binary search tree. One is the node. All the circles are nodes, right? We call it node. And of course, there are some edges, the links or edges. So this guy pointed to that guy, this guy pointed to that guy. All right, we call it edges, right? In graph, you can call link. It doesn't matter anyway. So it's a tree, and each of the node has only at most 2 children, right? And also the order is very important. For example, node B is the left child of A. And C is the right child of A. So at the most, if you check all the nodes, for each node, at most they have at most 2 children, cannot more than 2. Where for the one at the bottom, for example, D, E, H, those are at the bottom. They don't have any children, right? So for those nodes, we call leaf or leaves, right? We call leaves. And for example, B got 2 children, got a left one, left child, right child, left child is D, right child is E, and C does not have a left child, but have a right child. And this is a left subtree. This is the left subtree whole lot. This whole lot, if you could look at the cursor, the whole lot is the left tree of A, and this whole lot is the left subtree, is the right subtree of A, right? So those are the concepts that terminology that we are used in the rest of the presentation today. This is actually a formal definition for binary tree. What's meant by binary tree? If we give a formal definition for those of you who are mathematicians, probably you like that one because it's very formal, right? So we actually use another concept called set to give a very formal definition for binary tree. If you got some trouble understanding that, no problem. Don't worry about too much anyway. So I can explain to you in plain English, right? So there's no problem, right? So if you look at this definition, actually this is a recursive definition. What do you mean by recursive definition? When we're defining something, actually we're defining a concept, we also use the concept. These are a recursive definition, as you can see. So first of all, as you can see from there, so a binary tree is a set T. It's a set. We use a set, right? It's a set of nodes such that number one, there T could be this set could be empty, which means a binary tree may not contain anything. So it's an empty binary tree, right? That's fine, no problem. All the set T can be partitioned into 3 disjoint subsets, right? We still use the set to define binary tree. So one of them, 3 parts, right? 3 disjoint parts. One part is called a node. It's called a root, a single root. For example, for this particular, this is the root. A is the root, all right? And the rest can be divided into 2 subset, right? So this is the one subset, this is another subset. This subset is called left subtree, this is called right subtree. Okay? And each of them, for example, each of the both left subtree and the right subtree are binary tree. So sounds a little bit confusing, right? So we use the binary tree to define binary tree. So this is recursive definition, right? So left-hand side is also a binary tree, right-hand is also a binary search tree. Both of them are binary trees. So this is recursive. Anyway, if you can't follow, if you don't like the formal definition, mathematical formal definition, don't need to worry about too much. But you do need to understand the concept, what's meant by root, what's meant by left subtree, right subtree, leaves, and so on and so forth. That's all. Now, talking about the most important one, called a binary search tree. The concept that I just talking about was a binary tree. Now I'm talking about a binary search tree. Okay. Then what is a binary search tree? A binary search tree is a binary tree. First of all, it's a binary tree. Okay, and also have some properties that the binary tree needed to satisfy. So what's the property? For if a binary tree is a binary search tree, then for each node, right, not just the root, for each node, for every node, for each and every node, for example, each of them, this one, that one, each node, you must guarantee the value, the nodes on the left-hand side of the node are less than or maybe equals to the value of that node. And all the value on the right-hand side of the node are greater than or maybe equals to that value. Not just for the root, for every node. So this is just an example. So for example, the left-hand side binary tree is a binary search tree, where the right-hand side is a binary tree, but it's not a binary search tree. Okay. Why this one is a binary tree, we can quickly verify. For example, each node, this does not have any left or right, so it doesn't matter, right? For this guy, this does not have any children either. So this have a left. For left, 30 less than 50 is fine, right? 55, there's a right-hand side of this node. I'm talking about 50, node 50, greater than this is fine. And if you look at this node, all the nodes on the left-hand side has the value less than or equals to 60, right? See, this is 60, they're all less than 60. And all the right-hand nodes are greater than 60, or could equal is fine, right? And this is not all. You need to check this node. This also, satisfy those properties, right? So this is a binary search tree, where this one is not. So even, for example, if you look at the root, all the nodes on the left-hand side less than 60, all the nodes on the right-hand side greater than 60. But if you look at this particular node, let's say that particular node, 75, the left-hand side node, the node in the left subtree is greater than 75. So the right-hand side one is a binary tree, but it's not a binary search tree. Okay? Any questions about the concepts? Binary tree, binary search tree. Okay, good. So that's pretty simple. So for binary search tree, typically we have, those are the typical, most popular operations defined on dot structure on the binary search tree. Binary search tree dot structure. Because binary search tree is also a container, so from time to time we need to check if the binary search tree is empty or not. So we have a is empty. So basically that operation is return a Boolean value. So if the binary search tree does not contain any node or is empty, then you return true, otherwise return false, right? Insert, you need to add one new one new item on one new node, right? If we use the concept for binary search tree, you need to add one new node into the current binary search tree. But after the insertion, after insert that node, you need to guarantee after the insertion, the binary search tree will still a binary search tree. I will give an example to talk about. We'll actually look at the insertion implementation in detail in a few minutes, right? And delete, the same, similar, I should say, not the same. So delete basically to remove one node out of a binary search tree. The key point is you cannot simply remove anyone. Giving, for example, a node, for example, the value of node, you need to search if the node is or the key is in the binary search tree or not. If it is, then you need to remove that node from a binary search tree. To remove is easy, but the challenge is how would you guarantee after removing a node, the binary tree still a binary tree? All right. Again, I will talk about in very detail. Search basically is giving an item. You need to check if the item is present in the binary, if in the binary tree, binary search tree or not. All right. And then those are the traversals. Three different types of traversals. We have already talked about traversal, right? So traversal basically is to visit all the nodes. For this, in this context, we need to visit all the nodes in the binary search tree. And during the visiting, we must guarantee for each node we visit once and only once. There's no node which will visit more than once. For example, visit twice or don't visit at all, right? We only visit once and only once. This is what we call traversal. So we have three different order, which I'm talking about in. We'll talk about in very detail. There are pre-order, in-order, and post-order. All right. And finally, we have clear. Basically, it's to get rid of all the nodes. It's to remove all the nodes from the binary search tree. All right. Now, how to, for example, if you have a binary tree, so how would you implement a binary tree? So you have node logical structure. So this is a binary tree. For example, give a binary tree like that, binary search tree like that. How would you implement that in your C++ program? For example, how would you do that? All right. So you need to hold the data, and you also need to maintain the relationship between those nodes. For example, 50 is left child of 60, and 70 is a right child of 60. You also not simply store those data 60, 50, 70. You also need to maintain the relationship between those nodes in your C++ program, right? How would you do that? So this is a solution, right? So we can use a pointer. We can use a pointer, for example. So we need to, if you we take another look, just to give you briefly another look of this one. So if we want to define, for example, abstract data structure to model binary search tree like this, which consists of a number of nodes, then we need to define another data structure, which is called something like whatever you call another class, new class, which model those nodes. So basically, you have a class, for example, binary search tree node, class, or ADT, or abstract data type. So each instance of the binary search tree node class corresponding to represent one node in the binary search tree. All right. So before we define ADT for binary search tree, we need to create another ADT or another class for nodes. So each instance of the class node represent one. Actually, it's represent one node in the binary search tree. Okay, so we need two ADTs, right? We start with the fundamental one, which is the ADT modeling those nodes. Just the one node, sorry. So this is how, right? This is the structure for binary search tree node. So as you can see, so we need to have, basically we have three fields or three data members. If we talk about in a model in a class, we have three class members. One of them is what we call the item, sometimes we call data, it doesn't matter anyway. So this is the field we actually store the information. This could be anything, right? The item could be, for example, a student record, could be an employee object, could it be something else? Could it be an integer? Right? Could it be a string? Could it be anything? Right? It's just an abstraction. Right? So we need a field to hold the information, and that field we call, for example, item. And we need because we also, in addition to the data, we also need to maintain the relationship between the nodes in the binary search tree. For example, who is the left child? What's the parent of our node, and so on and so forth. So we need to maintain this information. So actually, that's why we have another two fields or two data members. One is we call left child. Left child here actually is a pointer. We use a pointer pointed to its left child. And similarly, we have R child stands for right child. So which also a pointer pointed to its right child, right? So each node we have three fields, right? So we need to, for example, before we look at them in more detail, so how to build an ADT to model a node in a binary search tree. We look at, if we do this, how would we represent a binary search tree in a C++ program? So basically, this is how. Right, this gives you some idea, right? So this idea. For this one, so you have A, which is the data. So here is just the character, right? The data type is a character. Again, it could be more complicated. Actually, in the assignment, they could be something else. So we'll talk about next week. Right. So A's left child is B. So this pointer pointed to B. Right child is, as you can see from there, is C. So pointed to C. Right. And C does not have a left child, so this is a null. And C the right child of C is F, so this is F, so on and so forth, right? Yes?
So these containers are arrays?
No, this is the fundamental data structure. So this is the one where actually the information is stored. So we don't use any array, we don't use any other. This actually is a fundamental data, is a basic data structure. Okay. Okay, so this is the one. This where we actually hold data. For example, for vector, if the implementation is an array, the actual data structure, the physical data structure we actually use to hold the data is actually an array, right? So actually, for example, the first element in the vector is held in the first element of our array, right? Here is different. For binary search tree, the information is held in those nodes. So as you can see, A, B, C, D, those are the nodes. Those are the physical place where the information, where the data are stored. All right? So that's all. Now we talk about the modeling. We talk about how to build our class or ADT to model one node in the binary search tree, right? So just quickly, so here we use, for example, so to make this program need to be more generic. So that's where we use a type define. So I already explained this one, so I don't want to waste too much time, any time on that, right? So the type of data type, so this is a char, right? So if I replace it with something else, that's very easy. There's only one occurrence you can replace. For example, if the data type changes integer, you replace char with integer. If the data type is a student object, you replace this one with a student class. All right? Now, in this class, the class name is called the BTreeNode stands for binary tree nodes. 3 fields. One is the data. The type is the data type. Where is the data type? There's a right. So whatever you define over there, right? This is a data type. This is a pointer. Is a pointer pointed to another node, left child, right child. So this is a pointer type. Which pointer? A pointer to a node, to a binary search tree node, right? To another node. This is the pointer type. Now, those are the some public method function, I should say, in C++ defined in this class. So, for example, we have a constructor, right? We have a constructor which takes only one parameter, that is the item. That's the data. For this one, now it's data type. In general, it's a data type. You know, it's an item. Could be student, could be integer, could be char, could be anything. Another one is we need to get the item, right? Sometimes we need to access the item stored in the node, right? So that's why we have a function called getItem, right? And of course, we have a getItem. We also have a setItem. Sometimes we need to change the data stored in a particular node, right? That's why we need a setItem. And sometimes we need to get the pointer, the left child pointer. Sometimes we need to set left child pointer. Similarly, we need to get the right child pointer. We need to set the child pointer. So that's all we have. Of course, this is very important, and I should emphasize here. There's a destructor because we are use linked data structure, which means that they are dynamic. So we have to deal with the dynamic memory in the destructor, right? Here, all right? So this is pretty easy. Now, very quickly look at the implementation. The implementation, so this is a constructor. Constructor is to build an object. For this constructor, build an object of a BTreeNode, right? So this is initialization. The data type is initialized over there. The pointer, you can also put over there in the what I call, did you remember? Colon section, right? This is a colon section. Sometimes when we initialize, this is something that C++ is different from other program languages, right? Sometimes you have to, well, this is really depending on the type of item, right? The type of item, for example, is a pointer type. You would have to use a colon section. Otherwise, you don't have to. For example, for those other class members, you can initialize like this. That's fine. All right? And get, so it's pretty easy, right? So get the item. So simply return that item. So the return type is data type. Set item, right? And similarly for the 2 pointers, left child pointer, right child pointer. So we have a mutator and accessor for each, right? So this is how. This is pretty straightforward, right? Finally here, for this one, each object of a BTreeNode contains three, as you can see from there, contains 3 class members, right? Contains 3 class members. So the question is, if any of them inside of this node point, actually use some dynamic memory. So this is the point. And also I need to be confusing. For this, I draw a diagram for you guys. This is the one object of a B-tree type. which contain, for example, let's say currently is a C, is just an example, is a child type. So this is a pointer pointed to somewhere, pointed to another node, which is the left child of C. And there could be another one pointed to maybe another one child, which is a right child of C. But this part, this basically is the object of B-tree chart, right? So for this one, when we destroy, so this is the only one, this does not contain any, for example, this is not a part of, this is not, so this is very important, this is not a part of this object. We only have a pointer pointing to another object, but this is not a part of the object. This is not a part of the object either, right? So when we destroy, so we actually, if you look at this object, this actually does not contain any dynamic memory, right? So that's why for the destructor we don't need to do anything, right? For that one, but for binary search tree, which contain multiple nodes, as we were saying a minute, we need to delete all the nodes in the binary search tree one by one when we destroy our object for binary search tree. All right, so we need to make it very clear, right? This is very confusing. So why? Oh, this is a direct pointer. Why we don't need to worry about that? Why we don't need to delete that? Because the scope, right? So this is the current. When you, for example, destructor destroy object, this is the object to destroy. So you don't want to destroy the other objects, right? You only destroy your own, this current object, all right? Okay, binary node. Okay, now we look at the most important part. I said earlier, in order to build a ADT or class to model a binary search tree, first of all, we need a fundamental basic data structure to a basic class, a basic ADT or class to model those nodes in a binary search tree. Basically, each object of binary BTreeNode model one node in binary search tree, right? Now, there's a second one. This is a more important one. Now, we need to define another ADT. We call it binary search tree or BST, right? So this basically is a class, as you can see over there. So each class, each object of a BST class. So as we'll say in a minute, the BST will use BTreeNode. Okay, we will see in a few minutes. In a second, actually. Each object of BST class model represent one binary search tree, which consists of number of binary tree nodes. So you got to distinguish, you figure out their relationship. Otherwise, you're probably confused, right? And in the binary search tree class, this is the most important one. The top one, the highlight one in red, is the most important. There is a pointer pointed to the root of the binary search tree node. Okay, that's why BTreeNode type of pointer, because it's pointed to a node of this type, right? So it's a pointer pointed to a node of this type. It's a pointer type. Don't forget it is a pointer, all right? The rest on this slide is just some private functions, which I will tell you, talk about later on. So don't worry about the rest. Okay, these are private. All right, this is not public. So those are not accessible from outside. Those are just some private functions. We'll come back look at this one. We'll look at the public one first, right? And similarly for binary search tree, we have of course we have a constructor. We must have a constructor, right? So we have actually this constructor is we call it default constructor, right? Because that's not take any parameters. It's called default constructor. This is used to create an object of BST or binary search tree. So this is empty. So the return type is a Boolean. So this is a const, which means this function does not change any value of class members. There's only one class member value, which is root, right? So this function will not change. This indicates we are not changing that class member value. Does not change root, all right? So why we use this good practice? I talked about before, because this is about protection. So if, for example, because the designer of the ADT may not be the implementer of the ADT, right? You could design our ADT and get somebody else to implement it, right? So if the implementer, for example, when they implement isEmpty function, they try to change root, the class member root as a value, the program will not compile, right? That's why. So this is a good practice. So the const used here is different from the const used over there, right? So you guys should be able to distinguish them, right? Insertion, just insert data item. This const indicate when we implement insert, these parameters value will not be changed. So these parameters value, these are const. These parameters value will not be changed. That one is empty const. That const indicate the class members value will not be changed. Okay, so this is a difference. So this is an insert. Okay, and also I probably need to spend a little bit of time talking about. Did you guys know design by programming or design by contract? Did you know the concept? No? Okay. Design by contract is sort of, how could I explain this concept to you in just a few words? Basically, it's design technology, right? The basic idea proposed by BTreeNode, which is a big IT guy, so he's still in the United States somewhere. And initially, that idea is designed by contract was proposed in a programming language named Alpha or something like that. Anyway, this is not very important. The important is the basic idea behind the design by contract is they treat the relationship between the ADT user. So, for example, if we are design ADT, right, it's a reusable ADT. Of course, they could use it by yourself, could be reused by somebody else in other systems, in your system, in other system, in anywhere. This is a reusable ADT or reusable class. This is what we call the ADT provider. There's another concept, which is a client. So client is just the user of the ADT. For example, you design an ADT, which is a reusable, could you use it anywhere, and when I develop a system, I found, your ADT is very useful, so I want to use your ADT. So I'm a client of the ADT. I'm a user of the ADT. We call it a client. In design by contract, they treat the relationship between the ADT provider and the client as a sort of they call it sort of contract. There's we sign a contract. So the contract just specify the two parties' responsibility and obligations, right? So for example, I just use this one as an example. So for example, for each of them, basically, for each of the key idea behind design by contract is for each of the operation. They talk about in general sense, operation. In this context, for each of the functions, class member functions, we need to specify the precondition, post-condition. And for all the class, we need to specify what's the class invariant. Okay. Now we don't use the class invariant here. We only use the precondition and the postcondition. Precondition, what do you mean by precondition? Precondition means, okay, I'm a designer, I'm an ADT provider. I design the ADT and I implement ADT. I provide it for somebody else, for you to use. But when you use, I need to specify there's a precondition. So the condition, for example, for this function, the condition must be true before you must guarantee when you use myADT, or for example, this particular function, you need to guarantee the precondition is true, or the preconditions are true before you can use that function. So if the preconditions are true, I can guarantee to provide the service that are provided, that are specified in the post condition. All right? If the condition not true, I cannot guarantee. May not work. I don't know, but I cannot guarantee. So this is sort of agreement. It's a contract, right? So when one client use, for example, that party function, if they can guarantee condition true, we can guarantee the post condition. We can guarantee we can provide the functionality, maybe the service, specified in the post conditions. So, for example, when we say true precondition true, we mean there's no precondition, there's no condition for using that particular function. So, and the post condition is if we, when we make our call, this function item will be added to the binary search tree. So we can guarantee. And we guarantee after the insertion, the binary search tree is still binary search tree. Okay? So this is basically the idea, right, in precondition and post-condition, right? So if because of time limitation, I don't think I have enough time to talk about class invariant, which probably I need a bit tricky, need a bit more difficult concept to understand. So I would suggest you guys after the lecture, for those of you who don't know what's meant by design by contract, and this is a terribly useful design technique used in today's IT industry, right? Very popular. So you should know that, right? But this is not covered. Basically, not covered in this unit. But I think it's very important. So you can do a quick search over the internet and say, using the keyword design by contract, you quickly, there could be some more meaningful examples over there. Anyway, so this is precondition and post-condition. So this is for insertion, for delete. So we have already talked about search a binary search tree, traverse, 3 different traversals, pre-order traversal, in-order traversal, and the post-order traversals, right? And then destructor, and also clear, that's to get rid of all the nodes in the binary search tree. Now, before we look at the implementation one by one in detail, I'm talking about the algorithms. I'm talking about the three algorithms about traversal, right? So traversal, again, quickly recap what's meant by traversal. Traversal basically need to visit each of the nodes in the binary tree once and only once in this context, all right? So 3 different order. We talk about one by one. We start with pre-order traversal, right? So basically the job is we need to visit all the nodes in the binary search tree, and we must make sure for every node we only visit once and only once, right? So this is the challenging part. Then what's meant by pre-order traversal? Again, I'm using recursive definition here. So pre-order traversal means, first of all, when we visit those nodes, there are quite a few nodes in the binary search tree, and we visit a node, we always visit the root first. So for this instance, the root is A. We always visit A first. For example, when we say, for example, print out A first, right? Or maybe do something else, right? We visit A first, and then we traverse. See, when we are defining traversal, we also use a traversal here. We traverse the left subtree, which is this, right? Left subtree in pre-order. See, it's a recursive definition. So how could I traverse the left subtree in pre-order? Also recursive, right? So we visited the root, which is a B first. And we recursively pre-order, we use a pre-order traversal to visit the order node in the left subtree of B. And then we traverse the right subtree of B in pre-order. And then when we visit D, the same idea. We visit D first, and because D doesn't have any left subtree or right subtree, so stop, and then we visit E, right? So the order is, so, okay, one thing I should emphasize, this is very important, otherwise when you do the traversal, you may not get it right. For the traversal, I probably draw a diagram. So for this one, this is a pre-order traversal. So we visited, pre-order means we visit the root first. So we put root over there. Then we use the pre-order to traverse the left subtree of A, which is this. After visit all the nodes in pre-order, in the pre-traversal order, then I visit all the node in is the left subtree of A, which is this. Right. So now I'm visiting. I use the traversal idea recursively. Now is the time to traverse or to visit the order node in this subtree in pre-order. So similarly, I do the same. Pre-order, I copy here. Pre-order, I need to visit the root first, B. And the left subtree, and then left subtree, which is this. And the right subtree of B, which is that. And then visit the order node in the right subtree of A, right? This is not finished yet, right? Now now we use a pre-order traversal to visit all the node in this binary search tree. Because this binary tree contains only one node, of course. This is the only one we print. So we visit the node, which is the root, which is D. So we visit D. Similarly, when we visit this one, which also contains only one node, we'll visit the root first, which is E. So we visit E. Right? So now I have visited the root and also visited all the node in the left subtree of A in pre-order. Now it's time I use the same idea to visit all the node in the right subtree of A in pre-order. So you cannot change the order pre-order. So the result would be what? Root first. See? This root, right? After I say left subtree is empty and the right subtree, this is the right subtree. Right? When we use the traversal, pre-order traversal, we always visit the root first, which is F, and then G, and then finally H. All right? So if you draw a diagram like this, you cannot get wrong, right? So if you use this idea. So when you're very comfortable with the traversal, of course, you don't need to draw a diagram. You can directly jot down the order. Okay? So that's the output from that one. That's a pre-order traversal. I show you the order. So initially, we always, for pre-order, we visit the root first. And now we are recursively visit all the nodes in the left subtree of A in pre-order. So how to do that? We visit B. The root is B, right? The left subtree, root of left subtree is B. And then we use the idea, we visit D, and then E. Now we have visited all the nodes in the left subtree of A. Now it's time to visit all the nodes in the right subtree of A. So the root always start at the root because pre-order, right? And then this one, and then that one, and then finally E. So this is how it works. Any questions about pre-order traversal? No? Okay. So this is the implementation. The implementation, as you can see, the top one, this is the public function. This is the public function, where this is actually a private function, which I define here. So I didn't talk about that, right? So this, as you can see, there is a PreOrderTraverse, which take one parameter. That's the root of the tree, right? So that's one. And for the public one, Traversal, the public one, this is the public one, Traversal does not take any parameters, right? So now this is the public one. Now when we define the public one, this is the public one. The top is the public one, which does not take any parameter. We just make a call to the private PreOrderTraverse function, right? This is the call. And then we make a call, because this is a function call, we pass the root of the binary search tree to this second function, private function. And as you can see, okay, this is a recursive function. We talked about recursion earlier, right? So this is a recursive function. For recursive function, first of all, we need to check if the root pointer is 0 or not, or if the binary search tree is empty or not. All right? If it's not 0 or if it's not empty, then first of all, we visit. Once I visit here, I mean I print it out. I visited the root. So how to print it out the root? So we use a cout root. This is a pointer type. That's why we use this notation. We use a pointer get item to get the root, right? To get the item stored in the root node, right? So this is why. The reason why I highlight that one over there is, did you remember we talked about another C++ technique called operator overloading, right? So for extraction or insertion, this is called insertion, and extraction, which are both of them are defined, the two operators defined in IOStream class, right? Basically, they don't work for user-defined type. They work for integer, the standard data type, integer, string, double, whatever, right? But basically, the insertion and extraction do not work for user-defined types. If you want to work for the user-defined type, you would have to override that operator, this operator, in which class? In this corresponding class, which is BTreeNode. Okay, so if here the BTreeNode is fine with this example because in the BTreeNode, this just the this is a pointer get item which return our char type. Is a char, which is a fundamental data type. So we don't need to override. If the type of the element, if the element stored in the node, BTreeNode, change into a student, for example, which is an object, then you need to overload this operator in the student class. Otherwise, they wouldn't work. Right? We're talking about operator overloading. Right? So this is why I highlight over there. Okay, now we visited the root first because of the PreOrderTraverse. And then we recursively visit all the node in the left subtree. And then after we visit all the node in the left subtree, and then we visit all the node in the right subtree, both in pre-order. All right? So this is the way. So as you can see, otherwise without a recursion, if you write a function like that, probably it's not easy, right? If you use a recursive function, so only 3 statements, right? So it's very simple. And the logic is very clear, right? It's very easy. So once you're comfortable with recursion, it's a very, very good program technique, all right? Okay, any quick questions before I take a 10 minutes break? All right, let's take a break first. Oh, sorry. Okay, now, before the break, we're talking about pre-order traversal for binary search tree. Now, talking about the other two traversals, which once you are comfortable with the pre-order, it should be very easy to understand the other two traversals, in order and the post-order traversal. So you probably can guess what's meant by in order. So this is the formal definition. So for in order, it's different. Pre-order, so we always visit the root first, and then recursively traverse or visit all the nodes in left subtree, and then after visit all the nodes in left subtree, then we visit all the nodes in the right subtree in pre-order, right? So this is the by definition. Well, for in-order traversal, we traverse all the left subtree, all the nodes in left subtree in order first. And then we visit the root in the middle. Okay, we then visit the root. And after visit the root, and then we visit all the nodes in the right subtree, right? So this is what we call the in order, right? So in order means, for this particular example, we need to use in order to traverse all the nodes in the left subtree, which is this first, all right? And then we visit the root, which is A. And then after visit all the nodes, traverse all the nodes in the left subtree and the root, and then we visit all the nodes in the right subtree in order. All right? So similarly, you can draw a diagram, right, like that. So for this one, okay, let's start very beginning. So this time we get the output, right? So for this particular instance, if we use in-order traversal, we need to visit all the nodes in left subtree first, which is this, right? So when we visit all the nodes in this binary search tree, we need to do the same. We need to visit the left subtree of B first, right? Which is D, so we'll print out the D. And then we visit the root, which is B, right? So print out B, the second one. And then we'll visit E. Now we have visited all the nodes in the left subtree of A. It's time to visit A, so then we visit A. So A in the middle, and those nodes on the left-hand side of A are the nodes in the left subtree, right? Now we use the similar idea to visit all the nodes in the right subtree of A, right? Which order should we visit the left subtree of A? This is the root of the left subtree. C is the root of the left subtree. The left subtree is empty, right? So we directly visit C. This is C. So after A, we visit C. And then we use in order to traverse the right subtree of C, which is this one, right? So the left subtree is this one. Left subtree of F is this one. We need to visit all the nodes in the left subtree of F first before visiting F, right? So we need to do this. How to visit this one? G does not have left subtree. So we visit G first, and then right subtree, which contains only one node, H. So we output H, we visit H, and then finally we visit the root, which is F. So this is the output. All right? So this is the order. Anyway, so now visit the root, left subtree. So this is the order. So this is the implementation. The implementation pretty much the same. The only tiny difference is here in the recursive function. Here is the same, right? But this time we make a call to in-order traversal, which is our is a private function defined here, right? So when we use actually for this private function, this private function is a recursive function, right? But here it's pretty much the same except for the order. So we traverse function recursively call itself, right? To visit all the nodes. So this passes the root of the left subtree. Visited the root and visited the right subtree. So when we visit the right subtree, we pass the pointer pointed to the root of the right subtree, right? So then this is the in-order traversal. Okay, so post-order traversal. So now you already know. If I don't tell you, you shouldn't know. In a pre-order, we visit the root first. In order, we visit the root in the middle, right? And post-order, that's indicate we visited the root last. Okay, so the idea is, so I don't want to waste the time in talking about the definition again because I already got the idea. I just use this example to demonstrate how to do post-order traversal. Post-order traversal means for this particular instance, we need to use the post-order to visit all the nodes in the left subtree of A. And then we use the post-order to visit all the nodes in the right subtree of A. And finally, we visit A. So A always visits the root, always visits last. Right, that's the last. Right. Then how we use post-order to visit all the nodes in the left subtree, the same idea. We visit the left subtree, which only contains one node, D. Right, we visit D first, and then we use the same idea to visit all the nodes in the right subtree of B, which also contains only one node, E. So B, E, finally B. D, E, finally B. Right? Now we have visited all the nodes in the left subtree of A. Now it's time to visit all the nodes in post-order traversal. In the post-order, all the nodes in the right subtree of A. We use the same idea. How to do that? The left subtree of C is empty, so don't need to worry about it because there's no nodes in the left subtree of C. Now it's time to visit all the nodes in the right subtree of C using the same idea. Right? So this now is current root, right? The root left subtree is this one. Right subtree is empty. Left subtree, how to visit this one? Left subtree of G, empty, right? Right subtree contains only one node, H, so visit H first, and then finally visit D, right? Now we have visited all the nodes in the left subtree of F, then we visit the right subtree is empty, so we visit F, and we use the same idea. The left subtree empty, right subtree already visited, so time to visit the root, which is a C, the subtree of, and then finally we visit A. All right? So this is the post-order traversal for binary search tree. Of course, but this can also use it for binary tree as well, not just limited to binary search tree. All right? There are some important properties. For example, if we use in-order traversal, just to give you an example. For example, if we use in-order traversal, you can say, the in-order traversal example is not a binary search tree. If it is a binary search tree, when you print out the node actually is sorted in order, is put in order, okay, in ascending order. But this is not a binary search tree, because traversal not just use it for binary search, they can also use the binary tree as well. And this is just an example of a binary tree, not a binary search tree. If this example is a binary search tree, when you output, the output, if you look at the output is sorted, is in ascending order. So this is one of the properties for in-order traversal, right? Anyway. Now we look at the other operations defined in binary search tree. So this is search, right? Search is similar to binary search in a vector, in an array, which you have already talked about, very similar. We use the same idea, right? So if we use a binary search in an array, what did we do? We compare, for example, we have a key, we'll compare the key with the key in the middle element in the middle. If they are match up, we find the element, right? We return the index. Otherwise, if the key is smaller, then we search the left-hand side. We don't need to worry about the right-hand side. We just cut the search space by half, right? So we use the idea recursively. Now, the same idea. So for this one, so these are binary search tree, right? Now, for this binary search tree, this is something you have implement this binary search tree in your C++ program, right? But you cannot see. It's not visualized. You cannot see. For example, if we search for 80, you don't know if 80 is there, is present or not in the binary search tree or not. You don't know, right? How would you do that? For a binary search tree, the only entry is the root. Is a pointer to the root. That's the only entry, right? So we always start from the root. You cannot jump from middle somewhere into the binary search tree. You cannot do that because the only entry is the root. So you always start from the root, right? So we start from a root. So the key we're looking for is 80, where the y in the root is 60. Because 80 greater than 60, so if 80 is in this binary search tree, it has to be in the left subtree of 80, right? Because greater than, right. It has to be in the right-hand side because greater than 60. It has to be in the right-hand side, in the right subtree of 80, right? So then we further compare next one. We'll compare this one first because greater than 60, so we go this one, we compare with this one. 80 also greater than 70. So if 80 is in this binary search tree, it has to be in the right-hand side, in the right subtree of 70. Then we further compare, we go to the right-hand side, into the right subtree. So we compare this one, this 80 match up, then we return, for example, the pointer to the node or doing something else, right? So this is search. So this is a situation, is a scenario where the item we are looking for is present, is in the binary search tree. So this is the order. There's another scenario, so where the item or the key that we are looking for is not in the binary search tree. So that is an example. So we always start from from the root of the binary search tree. For example, the key we are looking for now is 79. So we compare with the data with the key stored in the root of the binary search tree, which is 6 for this instance. Because 79 greater than 60, if 79 is in the binary search tree, it has to be in the right subtree, right? So that's why we go to the right-hand side. We compare with the root of the right subtree, which is 70. So 79 greater than 70, then we go to the right-hand side, right? Because of the same reason. Now, 79 is less than 80. So if 79 is in this binary search tree, it has to be in the left subtree of 80. So that's why this time we go left-hand side. So we compare with this one with 70, with 75, because 79 greater than 75. So we compare, we go to the right-hand side. But right-hand side is empty, which means 79 is not in the binary search tree, right? So we can return something. Okay, so this is the one I just showed you, just the basic idea behind the search. This is actually the search algorithm. Basic idea behind the search algorithm. This actually is the C++ implementation, right? So we use the same style, same structure. So because we use recursive function here again. So there are two search functions. The one at the top is the public one. The one can be used by client. The bottom one, the bottom one is our private function, which is used by the public search function only, cannot be used from outside because it's private, right? So, and this public one actually make a call to the private one. So public one take one parameter, private one take two parameters, right? Public one is the key or the item that we're looking for, right? This is the only parameter. Where for the private, there are two parameters. The first one is the key or the data that we're looking for, where the second one is the root of our binary tree. Okay. So first time we'll make a call if we search the item in which binary tree. The binary tree pointed by root. Root, did you remember? Root is a class member. It's the only class member of a BST class, right? We always start from there. This is the only entry. This is the only information we can flow. So we pass this one. That's indicate we search the item in that tree. You know, the tree pointed by the root pointed by this point. Actually, it's a pointer, right? Okay, now here when we search that one, so we search that one. First of all, we need to check if the pointer is 0 or not. If a pointer is 0, that's indicate now the binary search tree that we're inside we're searching for something is empty because the root is so if this condition is not true, if it's 0, then we return false immediately, right? Because indicate the item that you're looking for is not in this binary tree pointed by this pointer, right? From that root. Okay. Otherwise, if it's not 0, if the pointer is not 0, then we check, we compare with that node, right? We compare with that node. Basically, this is initially, of course, is the root. We start from the root, right? If it's equal, we return true, indicating, we found that one. That the element we're looking for is in the binary search tree, so we return true. Actually, that's it. We don't indicate the position or location, whatever. And otherwise, we check if the item is less than the right-hand side one. If less than right-hand side one, then that's a recursive call. Then we return. Then basically, if less than the right-hand side one, then we search the. If it's less than the item, then we search the left subtree, right? How to search a left subtree recursively? So item is still that item. We pass the item to another function call. But this time the root is different, right? The root is the root of the left subtree. If the item is greater than that one, of course, then we go another direction. We search the right subtree. We check if the item is in the right subtree. So this is a pointer pointed to the right subtree. And that is a pointer pointed to the left subtree, right? So we use this, again, this is a recursive function. See, this is a function search, so which take 2 parameters. We make a call to that function. We make a second recursive call to that function, right? This is a recursive function. So this is about the search. So this is just an example for this demonstrating. This is pretty easy. The one we're looking for is 45 less than 60. Then we go to the left-hand side, 50, 45 less than 50. So we search the left subtree of 50, right? So we go this way. We compare this one. This is the current item. This is the current root. The pointer pointed, the red pointer pointed the current root. right? This is the root. So we compared it with the root first, 45, 30, 45 greater than 30. So if 45 is in the binary search tree, then it has to be in the right subtree of 30. But right pointer is 0. So, oh, sorry. There's not a search anymore. This is an insertion. Okay, that's good. Okay, I'll talk about this is an insertion. We're talking about insertion now. I saw that this is another example for search. I was wrong, sorry. What we're talking about is just another one. We haven't finished the searching. So this one, we're talking about insertion. Insertion. So this one. The insertion, the challenging part is, as I said earlier, after insert one new node into the binary search tree, you must make sure the binary search tree is still a binary search tree. It's still in order, right? This is the challenging part. Okay, let's do it again. This is our insertion. So of course, the first, we need to find a right place for 45. Why I say right place, I mean right location, right place, I mean after inserting 45, the current binary search is still binary search tree. This is what I mean by right position. So the challenging part is where I can find a position for the new item, the new node, right? The new node is 45. So of course I always start from the root. So 45 less than 60. So if we insert 45, of course we have to insert in the left subtree of 60, right? Because less than 45. So it's the same idea. We compare this one. So 45 less than 50. So the top one was 60. Now it's 50. It's less than 50. Then we need to insert in the left subtree of 50. Okay? And then we do further comparison. 45 greater than 30. So if we insert into that subtree, that's the root. Currently the root is 30 into this subtree. It has to be in the right subtree of 30, right? But right subtree now is empty. So we can simply just insert that node as the right child of 30. So as you can see, after the insertion, we can guarantee this is still binary search tree, right? Still in order. So you can verify for each node, all the nodes in the left subtree less than or equal to the node, all the node in the right subtree greater than or equal to the root, right? So you can verify, you can check every node. So it's still a binary search tree. All right, this is about the insertion. So now the insertion algorithm. Okay, very quickly because we have another one, quite a few to talk about. This is insertion. This is insertion implementation. So basically, this insertion call another. There are two insertion. There are two insert functions. This is the public one. We implement the public one. Actually, make a call to our private one, right? This is also recursive function, right? So how to insert this one? We create a new object of what? Of a B-tree type, because we need to create one object. Each object of B-tree type represents one node in the binary search tree. So we need to create one object of binary tree node to hold this information, to hold, for example, 45. That's the one we used, right? And then we make a call to this insertion to insert this one, the new item, into the root. In the root, this is the binary tree root, right? So this is a recursive function here. So of course, the insertion, the challenging part is to find a location where we should insert such that after insertion is still a binary search tree. So this is the one. So of course, for this one, I highlighted for the same reason. So if the item is fundamental data types, like an int, it doesn't matter, you don't need to do anything. Otherwise, you need to override this operator in the corresponding class, right? For this one, that's the binary tree node class. Otherwise, it wouldn't work, or maybe give you a wrong result, right? So you just do comparison. If less than the item, and then you do your further check. If the right, you check if the right, if the left subtree is empty or not. If the left subtree is not empty, then you insert the node, the new node we just created, right? We created here. We create a node here and insert that node in the left subtree. This is a symmetry. So otherwise, we do the same, but this time, if greater than that one, and then we go this way, right? We create a new node here, and then we insert the new node of a binary tree node into the right subtree. Right? So this is the recursive function. Okay, now very quickly, talking about one last. We only look at this one because Kinnear and others are pretty straightforward. This is probably the most difficult implementation. For delete means just to remove one node out of a binary search tree. Again, the challenging part is after the deletion, you must make sure the binary search tree is still binary search tree. So for this one, there are 3 situations we need to consider. The first situation is the node to be removed or to be deleted is a leaf, okay? Which means that node does not have any children, right? So a leaf is the bottom one of the bottom. And the second situation, of course, is the node to be deleted has only one child. Could be left child, could be right child, right? And the third, of course, has both children, right? Have 2 children, right? So now we look at the 3 situations. The first situation is the one to be removed is one pointed by PTR here. Is pointed by PTR. So this is the one to be removed, right? So this is the parent of this node PTR, right? PTR is a leaf, does not have any children, right? So to delete that one is easy. We can simply remove that one. We can change the left child pointer to 0. That's it, all right? But this is a situation where the one to be deleted is the left child. So we do the same for the right child. For example, this, if the one to be deleted does not have any children and is a right child of another node, for example, the parent node, then this is the situation before deletion, and that right-hand side is the situation after deletion. This is very simple. We simply change the pointer, the right pointer in the parent node into 0. Delete it. Okay, now the second situation. So if a node to be deleted has only one child, of course, it could be left child, could be right child, but the way we deal with them is the same. So for example, again, the PTR is a pointer pointed at node, which is this, to be removed, to be deleted, right? How to delete that one? We simply change the pointer so that the that pointer could be left, depending on which pointer pointed to this, and it could be left, could be right. If it's left, we change left. If it's change right, we change right. So that is pointed to this one, to here. Then we delete that one. So in this way, we can guarantee after deletion is still a binary search tree. So again, the left-hand side is the situation before deletion. Right-hand side is situation after deletion, right? So of course, this could be left-hand, again, could be depending on which pointer the user pointed to that node, PTR. Could be left, right, right. Left, we change left, right, we change right. Right. Okay, now the most difficult scenario is the node to be removed has 2 children, right? So this is the situation. How could we do that? What we do is, so there is one observation. let's say, so for example, PTR is the node. It's the pointer pointed to the node to be deleted. As you can see from the illustration, PTR has a left subtree and also has a right subtree, have both, right? Now, how could I delete it such that after deletion, it's still a binary search tree? Okay, there's one very important observation. So what we do is, very important, we find, first of all, we find the rightmost node in the left subtree, which is this left subtree of a PTR. So the whole lot is the left subtree of a PTR. We find the rightmost one, which is the highlight one. Because it's the rightmost one, this guy does not have any right child. Otherwise, it would not have rightmost, right? But it may not have a left child, all right? Okay, so what we do is, why we are interested in the rightmost one? Because the rightmost node is the largest node in the left subtree. All right? Because it is the largest one in the right subtree. So we can actually, instead of delete that one, we can use that one to copy, to override the PTR one. We can use the highlight one to override the PTR, copy, to override. Okay? And because this is a single child, so we can use the single child deletion idea, right? Depending on who is this guy's parent. If there's a left child, if there's a parent pointing to this one, we only, there's of course that should be a parent. We find it's a parent, right? So that we use the single child deletion technique, which I talked about already. We actually deleted that one, and then copy that one to override this one. So in this way, we can actually delete the one pointed by PTR. So this is the idea, all right? So the key point here is how could we find the rightmost one? And once we find the most one, actually the node to be deleted is the rightmost one. But before you delete the rightmost one, we need to copy the information. We need to use this one. We need to copy the information to that one to override that one, and then remove that one, which has only one child. All right? So we transform our program to, of deleting a node which has two children into a program delete a node which has only one child, right? Which is easier. So this is the idea. So this is the implementation. So I probably have to skip this one because there are a couple of more new concepts. We need a new data type, new data structures we need to talk about today. So this is the implementation details. There are some comments over there, so you can see which is the case 1, which is the case 2, which is the case 3. For example, this is case 3, right? How to do that. Once you know the basic idea behind the deletion, you should be able to understand the code, right? The code should be easy if you got the idea. Okay, so there are some others, for example, the destructors and so on and so forth. And also there's another program demonstrating how to use BST or binary search tree class, all right? And also I have leave this one to you, for example, what happens if a binary search tree is not balanced, right? So this one. Now I move to another one. This should be very quickly, right, because it's only concept. Now we talk about a tree. So binary search tree, in binary search tree, every node has at most 2 children. Where for tree, that's a general tree. They could have many children, right? So this is an example. So there are many applications. For example, if you look at the structure, the file and the folder organizing structure in your computer, actually it's organized in a tree, right? For example, you have something stored in the root of your directory, or folder, right? And in the root directory, there could be some folders. We have some files directly stored in the root folder, right? And in each folder, you may contain some other subfolders, maybe some other files that are similar to this, right? So this forms our tree structure, right? This is just another example for tree structure. This family tree is similar, right? It's also a tree structure. For example, if you want to use a dot structure to represent a family tree like that, so you need to use a tree dot structure. That's what I'm talking about, right? A few concepts I need to talk about. So one is the root. This is not new to you at all. There's an edge, we call it edge, linking associated to nodes in a tree. So this we call a node. And all the green ones are the leaves, right? So this is the bottom one. The similar. Okay, so this is the concept we have. What's meant by parent, what's by child. It's exactly the same with we use in binary search tree. We also, that's just the one new concept, which is sibling. Sibling means all the nodes which have shared has the same parent. This is sibling. So this is similar in the real world, right? And also there are another two concepts. One is we call it, sometimes we say the height of a tree. So this is the height of the tree, right? Starting how many levels, right? Starting from the root, right? So for this one, for example, height is 3. And another concept is depth. For example, this is depth 0, which of course has only one node, which is the root, right? And depth 1, depth 2, and so on and so forth. Okay, and the challenging part is, how would you store a tree like that into your C++ program? How to do that? Of course, the most straightforward idea is we also create a node for tree. For binary tree, in addition to the data field, there are other two. One is a pointer to the left-hand child. One is a pointer to the right child, right? But for tree node, how many pointers? Because our tree node may have multiple number of children, right? How many pointers you should reserve over there? You have to use the maximum. For example, in a tree, let's say the maximum, in one node, the maximum has 10 children. Then you would have to, for every node, when you build more than that one, you would have to use 10 field pointers, which waste a lot of space, right? Most of the pointer actually not used, are all 0. So because of that reason, so we are not actually build our one similar to the binary search tree. Now, with one node which have an item plus many pointers, because with a lot of space. Instead, we transform our tree into a binary tree. This is the key point. Because there is an algorithm, which we're not talking about today, which can transform tree and a binary tree back and forth. Given a binary tree, we can build a tree. Given a tree, we can build a binary tree. They are one-to-one correspondence. Very easy. Okay. So because of that, so we can make use of the transformation. So if we have a tree that we need to represent, we need to in your C++ program, you can convert that tree into a binary tree. And then instead of store the tree, actually you store the corresponding binary tree in your program. Okay, this is how. This is how. Say we use a binary tree. Okay, the binary tree we have an item, but now we call it K. It doesn't matter. You can still call it item. But in addition to the item, so that's the first field is the place where we store the data. Could be student, could be integer, could be anything. And we only have 2 pointers, not many pointers, only 2 pointers. The first pointer is the first child. If our one node has many children, we only pointed to the first child, okay? And the second one is the first sibling, right? Only 2. Okay, I just show you how to store a binary or tree into your program. So when we store that one, we can convert. We can use the way showing on the slide to transform the tree into a binary tree over there, right? So we store, as you can see, this is a binary tree, right? Because each node has only 2 pointers, maximum of 2 pointers, right? Actually, not a maximum. Actually, exactly 2 pointers. So this is you can redraw this one. This actually is a binary tree. So use this one, A. This is A. First child is B, so pointed to B, right? And A does not have any sibling, so it's 0. Now look at B. First child F, so pointed to F. B first sibling, next sibling is C, so pointed to C. C does not have any child, so 0. Have one sibling, which is E, so pointed to E, and so on and so forth. So in this way, we can transform our tree into a binary search tree and store it in your program. In this way, you can save a lot of space. All right. This is whenever we deal with a tree data structure, we always use a binary tree. So this is this technique used in IT. If we directly handle tree, probably it's not a very good idea. All right. And also we have traversal. We have breadth first traversal. Breadth first means we traverse, we visit all the nodes in depth 0, and all the node depth 1 from left-hand side to right-hand side, and the next depth 2 and depth 3 until we visit all the nodes. So this is what we call breadth first traversal, which is very easy to understand, right? And this is an algorithm, there is no implementation. And there is another one. I probably can use some time to talk about that next week. We have a depth first traversal. Depth first is different. We're always going down, always going down whenever we can until we hit the wall, right? So this is a depth first traversal. We visit A first, and then B, and then we keep going. For example, C. There's no way to go. We cannot further going down. Then we backtrack to here, to visit, and then going down again, right? So that's G, and backtrack to here, and edge, and go back here, and then back, and visit C, and so on and so forth, right? So I have to now just use 1 minute, to talk about the map. What is a map? This is the only thing I needed to talk about today. Just a concept, all right? So the only thing you needed to know is the concept. The rest will be done in the workshop today, right? So map is different. Map basically is a key value pair. So typically for data in a binary search, we only have one key or one data. For this one, we have a key item, key value pair, right? So there are some, this, okay, I'll probably use an example. So for the key value pair, we needed to store somewhere. When we build a map, so there's a mapping. Given a key, I can find the corresponding value, right? So this is the mapping. And of course, in map, the key cannot be modified, but you can modify the corresponding value. And also, we assume all the keys are unique, so they are different from each other, right? So this is one. And map could be empty, right? So those are the operations defined on the map. So for example, for the map also a container, which hold a number of key value pairs, rather than just a single item, right? So of course we have, for example, constructor, destructor. We have a function which uses to check if the map is empty or not. That empty. We have a size which gives the total number of items in the map. We have a content key. So this is something like a search. So given a key, we need to check if the key is present in the map, right? And also put basically is to add a key value pair into the map. If the key already present over there, you simply overwrite the value, change the value. All right. This put a get is just the retriever. Given a key, you retrieve the corresponding value. All right. And erase just the get right of all the element. So basically, so there are those are the actually